In the last video, we looked at decomposing vectors. We looked at the projection of a vector and so forth. Now we're going to put that together for a word problem. Well, we're looking at an example with a forklift. Okay, it talks about a forklift is used to offload freight from a delivery truck. Together, the forklift and the contents weigh 800 pounds, and the weight is evenly distributed among 4 tires. Only drew 4 because we're looking at this sideways. Okay, or a profile of it. The ramp is inclined 14 degrees from the horizontal. Okay, so here's my forklift on this ramp. Now, I usually exaggerate the angle a little bit here, like 14 degrees would be less. But I like to be able to put stuff in there and be able to see it whenever I write it, okay? So we have an angle of 14 degrees in there. I'm going to write in there. Okay. Now, part A. If we want to answer part A, let me go ahead and put that over here. Part A reads, write the force vector F in terms of I and J representing the weight against a single tire. Okay, so what they're saying here is we have a force vector F that looks like that. Okay, the force due to gravity here. We'll go ahead and call that vector F. And we're going to look at a vector also that is actually perpendicular to this ramp right here. Looks maybe something like this right here. Well, I didn't do a very good job of perpendicular, but let's try to redo that maybe. Looks something like that. And then we have a vector that's going to be parallel to this ramp like this, okay? Because really what we're trying to do is we're trying to take this vector F and then look at it as this part plus that part, or this vector plus that vector, okay? So in other words, we're decomposing it, okay? Let's go ahead and put an arrow there. That vector points like that, that vector points like that. Let's go ahead and call this vector F2, and we'll go ahead and call that vector F1. Now all that should be given to you with the problem, okay? I just went ahead and drew it in here. All right, so if we look at part A says, write the force vector F in terms of I and J representing the weight against a single tire. All right. First of all, if you have 4 tires and you have 800 pounds and the weight is evenly distributed like this problem said, it'll be 200 pounds per tire. All right. Now, what do they want me to do? They want me to write the force vector F in terms of I and J, right? Remember that the way you can write this in terms of I and J is you could say the magnitude of the vector times the cosine of theta times vector I plus the magnitude of that vector times the sine of theta times vector J, right? Well, what's the magnitude of F? How much is on each tire right there? We said that 200 pounds is, right? Times the cosine of theta. Well, let's fill in for theta instead of writing theta there. Let's fill in for it, okay? So think about your ramp and so forth, okay? Here's a drawing of your ramp again. Looks something like that. Think about vector F coming down like this, okay? Now, let's think about the angle that we're at. Vector F is at an angle of what? 270 degrees, right? So for theta, I'm going to fill in 270 degrees times vector I, plus the magnitude of F again is 200 pounds, times the sine of that angle again, 270 degrees, times J. Now, how do I know it's 270? Because it's pointing downward, right? So I've got to rotate around like that. All right, so let's see. What do they want me to do here? Do they want me to round? No, they don't want me to round or anything. Okay, so here we have 200. What's the cosine of 270 degrees? Would that be 0? Plus 200. What's the sine of 270 degrees? Well, isn't that -1? Well, I can't round anyway because this comes out exact, right? All right, so what is this? Negative 200 times vector j is how I could write vector f. So that's my answer for part A. What about B? Find the component vector of f parallel to the ramp. Round your answer to 1 decimal place. Find the component vector of f parallel to the ramp. So they're wanting a vector that's parallel to f. Parallel to the ramp. So parallel to the ramp would be like f1, right? And that is a component vector of vector f. So let's look at finding vector f1 here, okay? This is part B now. This is part B. So we're looking at finding this one that's parallel to the ramp. So we're looking at finding vector what? F1 here. All right, let's think about this for a second. I could look at this as F1 as the projection of vector F. Like, think about the sun shining this way now. I know it's kind of weird because we're at the bottom, but think about if I'm shining a light maybe this way. I could think of a projection of vector F onto this right here. Now, this right here is the ramp, right? And I don't have it named a particular vector. But I guess what I could do is I could say, let's use a unit vector that we learned about earlier during this section. Okay, so let's draw a unit vector on this. Having issues with my markers. Okay, we'll go ahead and call that vector u, okay? Let's break that down into terms of I and j, that vector u. All right, so vector u. What would that be? If I break it down in terms of I and j, wouldn't it be the magnitude of vector u times the cosine of theta times vector I plus the magnitude of vector u times the sine of theta times vector j? All right, so let's fill in here. Now, what is the magnitude of u? If it's the unit vector, how long is it then? It's 1 unit long, right? So I'll put 1 times the cosine of theta times I. Now, what is theta going to be? Well, let's be careful here, okay? If I think of my coordinate plane being right here, or actually, let me move it over. Think about my coordinate plane being right here. I need this angle right here for my angle theta. Now, what is that angle? That's 180, but back off what? 14 degrees, right? So what would that be? 166 degrees times I, plus the magnitude of vector u, again, is the unit vector, so the magnitude is 1, times the sine of 166 degrees times j, right? So that would be cosine of 166 degrees times vector I plus the sine of 166 degrees times vector j. All right, now what are we really looking for? We're really looking for vector F1. So vector F1. Okay, what did we say about F1? We can look at moving it here, right? As long as I don't change the direction and magnitude. But we said that's really what? The projection of vector F here onto vector u. So we're going to write projection of vector F onto vector u. Now, we looked at this in the last video, right? So what did we say about how we find this, the projection of vector F onto vector u? Didn't we say it is vector F dot vector u over the magnitude of vector u squared times vector u? All right, so let's do this calculation here. F dot u. Well, what was vector F? Vector F from the last example was what? Negative 200j or something? for vector f, and the last example was negative 200j, right? But couldn't I look at that as this 0 comma negative 200 like that? And it makes it easier for me to take the dot product. Now, you don't have to do it that way, but you can. All right, so if I'm going to fill in the top here, vector f, 0, negative 200, dot, vector u, well, vector u was this, right? But I'm going to write it just like cosine of 166 degrees, comma, sine of 166 degrees. So I'm going to write it in the form a comma b, okay? Its components. Over the magnitude of vector u squared, well, what is the magnitude of vector u? If it's the unit vector, it's only what? 1 unit squared times vector u. So times, what is vector u again? Cosine of 166, sine of 166. Oh, I'm at the very edge of my board there. All right, so go ahead and do the dot product here, okay, up top. And what is that? 0 times cosine of 166 degrees plus a negative 200 times the sine of 166 degrees, all over 1 squared, which is 1, right? Then we're going to need to multiply by the cosine of 166 degrees, comma, sine of 166 degrees. And right here, what do we get? Negative 200 sine of 166 degrees over 1 is just that, right? Then you need to multiply it by cosine of 166 degrees, comma, sine of 166 degrees. And if you end up doing that, let's see, what do we get here? We get something like approximately 46.9472 is my first component here. My second component is negative 11.7052. And that's F1. But they want F1 here in Alex in terms of I and J. And they tell me to round to 1 decimal place. So I'm going to write that as 46.9 times vector I minus 11.7 times vector J. There we go. Now that moves us to part C. Part C. Part C says, find the magnitude of force needed to keep the forklift from rolling down the ramp round to the nearest pound. Okay. Force needed to keep this forklift from rolling back down that ramp, okay? So what that's going to be is that's going to be a force this way to hold it into place, okay? You can think of somebody actually sitting there and holding it like that. I guess it'd have to be some superhero. All right. What would that be? That would be the same thing as vector F, but turn the other direction than vector F, okay? So that would be like the negative of vector, I keep saying F, I mean F1 here. Magnitude of this vector F, I'm sorry. Vector F1 going the other direction, okay? So it's like negative vector F1. Now, what does it want there? Find the magnitude of that thing. So I want the what? I want the magnitude of the opposite, or negative, F1, okay? So what does that mean? I want the opposite of this thing. What is the opposite of F1? Opposite of vector F1 would be what? Multiply this thing by negative 1, and you get negative 46.9i plus 11.7j. And if you take the magnitude of that, what does that give you? Square root of negative 46.9 squared plus 11.7 squared. And you calculate that, I don't think it tells us, oh yeah it does, it says round to the nearest pound here. So if we do this and round to the nearest pound, we get approximately 49 pounds. 49 pounds.